Hey everyone, this is going to be a recording of Recitation 12. I actually did chalkboard work on Wednesday in class, so I didn't actually record this, and I'm just doing this separately now. And so yeah, let's just talk about then what I covered in Recitation. There's going to be 4 examples, and yeah, let's just jump into it. So the 2 things that I talked about in Recitation 12 are the following. The first, we went through 8.4, which is the complex value trial. Okay, and so complex value trial, this was on the homework due before Thanksgiving, and it essentially is the following. So like any other diffie-Qs, right, in complex value trial, we try to solve problems that look like the following. So example 1, we have y double prime minus 3y prime plus 2y is equal to 5e to the x cosine 2x. Okay, and so what we can do then is, there is the annihilator method. Actually, before we actually jump into that, so you have some diffie-Q that looks like this. Step 1 is always the homogeneous. So you get the following, right? Solving the homogeneous, you get d equals 1 or 2. So y homogeneous is equal to c1 e to the x plus c2 e to the 2x. Right? So that's always step 1. So step 2 essentially is choose your guess for yp, right? And there are many different ways we can guess yp. The way that we emphasized in chapter 8.3 was this annihilator method, right? And in this case, what do we have? We have 5e to the x 2x, so we would guess something like yp is equal to a e to the x cosine 2x plus b e to the x sine 2x, right? And that would be the annihilator method, and you would plug it in to the original equation. So complex value trial then does the following. We take a look at the right-hand side, and we look at, so the right-hand side is equal to 5e to the x cosine 2x, okay? And we want to know where this 5e to the x cosine 2x can come from. And so we notice that, okay, this has it has c e to the a x cosine bx, right? And therefore, this comes from some root that is a plus bi, which in our case comes from some root, right? That's some root, that's a plus bi, so this would be 1 plus 2y, and our guess then, so yp, we want to guess a e to this root, which is 1 plus 2y times x. Okay, so if you compare the 2 guesses from the annihilator method to the complex value trial method, you're going to notice that the complex value trial method is a lot more compact, right? Because you don't have to deal with, let's say, here you don't have to deal with the product rule, right? Whereas up here, when you take your derivatives, you have to deal with your product rule. So we're going to roll with this complex value trial method guess for now. So step 3 in the complex value trial method is to plug back in to the original equation, which means that we have to take our derivatives, so yp prime, and now you just have to deal with the complex value numbers, right? And so the first derivative then is going to be 1 plus 2i a e to the 1 plus 2ix, and then the second derivative is going to be 1 plus 2i squared a e to the 1 plus 2ix. Okay, and then a little bit of side work. You see that 1 plus 2i squared is the following. That's equal to 1 minus, or 1 plus 2i plus 2i plus 2i squared, and so, or 4i squared. And so this is really negative 3 plus 4i, a e to the 1 plus 2ix. Okay? And there we go. We have yp prime, yp double prime. So now we want to plug it back into the original equation, which is y double prime minus 3y prime plus 2y. So y double prime plus 3y prime plus 2y is equal to 5e to the x cosine 2. Actually, so when you do complex value trial, you need to make the right-hand side also this 1 plus 2i x guy now. Okay, and that's because, right, the right-hand side we literally said comes from 1 plus 2i. So, yeah, so 5e to the x cosine 2x just gets rewritten as 5e to the 1 plus 2ix. All right, we plug it in, so now you have negative 3 plus 4i, a e to the 1 plus 2ix, plus 3 times y prime, which we have up there, 1 plus 2i, a e to the 1 plus 2ix. And then, oh, damn, this is a minus sign. Okay. So minus, be careful. And then plus 2 times y, which was a e to the 1 plus 2ix. And that's equal to 5e to the 1 plus 2ix. All right. So now we just got to simplify this. So this is just a matter of algebra. So 3 plus 4i, a e to the 1 plus 2ix, minus, this becomes 3 plus 6i in parentheses, a e to the 1 plus 2ix, plus 2, a e to the 1 plus 2ix, equal to 5e the 1 plus 2ix. All right, so now we want to group the like terms. So here you get minus 3, that's another minus 3, and then plus 2, so that's negative 4, and then you get 4i minus 6i, so you get negative 4 minus 2i, a e to the 1 plus 2ix is equal to 5 e to the 1 plus 2ix. Okay, and then we want to solve for a, which ends up being 5 over negative 4 minus 2i. And, okay, we want to rationalize the denominator, so we multiply by the complex conjugate, negative 4 plus 2i, negative 4 plus 2i. Okay. Pro tip, the denominator always becomes a squared plus b squared, so that's negative 4 squared plus 2 squared. That's going to be 20. And then the numerator is going to be negative 20 plus 10i. So this ends up being a is negative 1 plus 1/2 i. All right, I'm not quite done yet because now, right, so yp is equal to a e to the 1 plus 2ix, which is equal to negative 1 plus 1/2 i. And then what you want to do is we have to split up e to the 1 plus 2ix into e to the x times cosine 2x plus I sine 2x by Euler's formula, right? So this part is a, and then this part is that part, okay? And then now we have to FOIL it, right? And to FOIL it, we get the following. So e to the x, we'll multiply all of this out in front, and then you get negative cosine 2x, okay, and then plus 1/2 I cosine 2x, and then minus I sine 2x, and then plus, or minus 1/2 sine 2x. Okay, so So that's what we'll get. And then the last part, right, of complex value trial is to go back to your original solution, the original right-hand side, okay, which was 5 e to the x cosine 2x. And so since the right-hand side is cosine, so original right-hand side is cosine, that means take only the real terms. So we really only want to take the real part of this yp that we calculated above. All right, and so what is the real part? Well, the real part is everything that doesn't have an I. So that's going to be this part right here, right? Negative cosine 2x, there's no I there. And then minus 1/2 sine 2x. So the correct yp is actually e to the x times negative cosine 2x minus 1/2 sine 2x. Okay? And that is the real part of yp. If the right-hand side were sine, right? So if this instead of cosine, if this is sine, then we would take the imaginary parts and then we would drop the I in our particular solution. So we're actually going to see an example of that in the next problem. Okay, so that's yp. And then to finish the problem off, then step 4 is the general solution, and essentially y of x is equal to yh plus yp, and we have yh up here, right, and we just add it to yp, which we found right here, and then we're done. So that's complex value trial, an example there, and it's not really, so this first example, you could have done with annihilators, this annihilator method, it would have worked just fine. The product rule is a bit annoying to do, but you know, it's doable. You'll only end up having like 8 terms, I think, at worst for the y double prime. So it really comes down to, do you prefer having a lot of terms using the product rule, or do you prefer working with complex numbers? And I don't know, personally, having less terms with the complex numbers makes it easier for me to keep my terms in check, so I do prefer using complex value trial. But either way works well. So let's take a look at an example where you can get baited into using annihilators where complex value is actually the correct way to do the problem. So the second problem, we'll take a look. Y double prime plus 4y prime plus 13y is equal to 12 e to the negative 2x sine 3x. Okay, so step 1 is the homogeneous, right? And we see that d is equal to negative 2 plus or minus 3i, and therefore my homogeneous solution is going to look like e to the negative 2x cosine 3x, or c1, plus c2 e to the negative 2x sine 3x. Okay, so that's the homogeneous in step 1. And then step 2, right, is to guess yp of x. All right, so again, if you use the annihilator method, so if we use the annihilator method, right, we would guess yp of x is equal to a e to the negative 2x cosine 3x plus a e to the negative 2 plus b e to the negative 2x sine 3x. All right, but that's the wrong guess because this is captured in the homogeneous, since e to the negative 2x sine 3x, right? If you look at the a plus bi, the a plus bi's part of it is negative 2 plus 3i, right? And that's in the roots of the homogeneous with multiplicity 1. So we have to multiply all this by x. And so then yp of x, the correct guess ends up being ax e to the negative 2x cosine 3x plus bx e to the negative 2x sine 3x. And this, you don't want to be using this, right? Because the problem is y double prime, and when you take 2 derivatives of this guy right here, You have to use triple product rule because you have 1x, 2x, 3x's in the problem. You don't want to be doing that. That's going to take forever to do. You're going to have so many parts that you have to worry about. So instead, the correct way to do this then, or the better way to do this, is going to be using complex value trial. Right, so the right-hand side is 12 e to the negative 2x sine 3x, which comes from a root that's negative 2 plus 3i. Okay, so this comes from this root, negative 2 plus 3i. However, right, so then yp of x, we would guess a e to the negative 2 plus 3ix. But that doesn't really work, again, because 2 plus 3i, right, is inside the homogeneous, negative 2 plus 3i. With multiplicity 1, it occurs once inside the homogeneous. So then we have to take all of this and we have to multiply it by x. So the correct yp of x guess would be ax e to the negative 2 plus 3i x. Right? And this guess is, it's a little bit better, right? You don't have triple product rule, but you still have to use product rule. And we'll see that it actually works out decently well when we plug it into the original equation. So step 3 is to plug into the original equation. All right, so yp of x, this is our guess right here. So yp prime is going to be the following. So a is a constant that can come out in front, and then this is going to be e to the negative 2 plus 3ix plus, and then negative 2 plus 3ix e to the negative 2 plus 3ix. Right, got to use the product rule. So that doesn't seem too bad. And then y double prime, a still out here. The derivative of the first guy is just negative 2 plus 3i e to the negative 2 plus 3ix. And the derivative of the second guy, got to use product rule again. So if we take the derivative with the x first, then we end up with the following, right? The x just drops out since the derivative of x is 1. And then we hold the x constant and take the derivative of e. And so now we get negative 2 plus 3i squared x e to the negative 2 plus 3i x. Okay, so law of product rule, that's fine. Like, this is much better than what the heck this would end up being with the triple product rule. Just in general, if you have to take triple product rule, you're doing something wrong, or it's not the most efficient way. Okay, so what is negative 2 plus 3i? Negative 2 plus 3i times negative 2 plus 3i. That ends up being 4 minus 12i plus 9i squared. So that's negative 5 minus 12i. Okay, so this thing right here, this is really negative 5 minus 12i. And keep that in mind. So now my original equation was y double prime plus 4y prime plus 13y is equal to 12. And remember, we rewrite this as negative 2 plus 3i x. Okay, that's because that's what the right-hand side is. And then, okay, so now we plug it in. Yp double prime is up here. And you'll notice that these two terms are actually the same thing. This term and this term are the same thing. So we can actually just combine them. So this becomes negative 4 plus 6i e to the negative 2 plus 3i x, right? Plus negative 5 minus 12i x e to the negative 2 plus 3i x. And then what else? Okay, then you have to add 4 times yp prime, which is up there. Oh, and of course there's an A. I forgot that. There's an A on all of this, so this is really A, this is really A, and then this is 4A, e to the negative 2 plus 3ix plus, and then this becomes A, and then this is negative 8 plus 12ix e to the negative 2 plus 3ix. All right, and then plus 13 of the original guy. Plus 13 a e to the 8x e to the negative 2 plus 3i. Oops. X. Okay, good enough. So, okay, so we want to look at what like terms. So we want to group like terms. So first of all, so we'll take a look at just no x e to the 2 plus 3ix's. So here's a negative 4a, and then here's a positive 4a. And I think that's it. So they cancel each other. And this 4 gets canceled by this 4. Then here's a 6i, and I think that lives. Okay, that's cool. Okay, so now what? Now we take a look at here's negative 5ax, right? And this is negative 8ax, and then here's positive 13ax. So this, and this kill each other. Negative 12ix, and then here's a positive 12ix. So that and that kill each other. And yeah, so all my terms are dead except that 6i term. So we get then a 6i e to the negative 2 plus 3ix is equal to 12 e to the negative 2 plus 3i x. Divide both sides to solve for a. So do that just to make it easier to track what my steps are. So now a is equal to really 12 over 6i. And that's 2 over I, and if you multiply the top and bottom by negative I, you'll get this is equal to negative 2I. Okay, so A is equal to negative 2I. That means then yp of x is equal to negative 2I times x e to the negative 2 plus 3ix, right? But we got to rewrite e to the negative 2 plus 3ix in terms of e to the negative 2x cosine 3x plus I sine 3x. All right, and if we multiply this out, right, you get negative 2ix e to the negative 2x cosine 3x, and then minus 2i squared, so that's plus 2ix, or actually just plus 2x because the I squared is 1, so this is plus 2x e to the negative 2x sine 3x. Okay, and now what we see is that, okay, the right-hand side of the original guy was sine 3x, right? So the right-hand side, original right-hand side is sine, so take the imaginary term, and the imaginary term is the term that has the I in front of it. So it's going to be this first one with the cosine. All right. We don't care about what this, like, the trig term attached to it is. We only care about if it has an I attached to it or not. So, okay, so we're going to take that term, and therefore my correct yp of x is going to be negative 2x e to the 2x, negative 2x cosine 3x. And this is the correct particular solution. And notice that I dropped the I, right? There's no I here, and that's because when you choose the imaginary solution, you really only care about the coefficients that are not the i's. So you take everything that's not the I. That's just something we do. Don't worry too much about that part. So in general, your particular solution should never have imaginary numbers inside of them. Okay, let's see how I'm doing on time. So, oh, okay. So this is only 25 minutes. Definitely took a lot longer to do one of these problems in class. Okay, so that's how you do these complex value problems. I guess just to finish it off, step 4, the general solution. So y of x is equal to yh plus yp, and yeah, we have yh written above, and we just found yp. So when do we use complex value trial? Again, if you realize that your annihilator is going to be really bad, first of all, if you look at the right-hand side and there's a sine or a cosine term, then you can always use complex value trial. If your annihilator guess ends up being really bad or like really messy, then you want to use complex value trial. Usually the hint there is that you're going to have to use the product rule, or in the worst case scenario, like a triple product rule. So as long as you recognize that, then you're going to be good with using complex value trial. So, okay, so that's complex value trial. What I'm going to do next then is an optional topic that Davi is not going to cover in class, but I'm going to cover it just because it'll expand your toolbox of the available methods that you have in solving differential equations. So it's chapter 8.7. It's called Variation of Parameters. Okay, and let's just jump into a problem and see how variation of parameters works out. So if you remember in last week's recitation, we took a look at a problem that looked like the following. Y double prime minus 5y prime plus 4y is equal to 7x e to the 4x, right? So again, step 1, we solve for the homogeneous, which always is the case. So you get d is equal to 1 comma 4. So yh is equal to c1 e to the x plus c2 e to the 4x. All right, so nothing should be provocative there. And then step 2 was when we had the whole guess thing, right? When you use the annihilator method, we have to guess y at yp, right, is equal to, and you have to guess a e to the 4x plus bx e to the 4x, right? And that's because there's an x term here, so we have to add up to that. And the problem, remember, was that this a term is inside the homogeneous right here. So in order to work around that, because this 4 is degree 1 or multiplicity 1 inside the homogeneous solution, we have to take this and we have to multiply by x to the first, right? But instead of writing x to the first, we're just going to write x. So, okay, so this is yp, so then yp really was ax e to the 4x plus bx squared e to the 4x. And then you had to work this one out. Using product rule, okay? So what variation of parameters is we guess the following. We guess that yp of x is equal to u1 y1 plus u2 y2, okay? And what is y1 and y2? Well, y1 and y2 are the parts of the homogeneous solution that we found. So we can call that guy y1, and we can call e to the 4x y2. Okay, so that's going to be u1. That's going to be y1 and y2. And so essentially, then instead of taking product rules and taking the derivatives of yp, we're actually concerned about finding what u1 and u2 are. And so to find u1 and u2, we actually turn, so step 3, right, is to find u1 and u2. So this is where it differs from what we've been doing so far. But to find u1 and u2, we're going to turn to integration, okay? So we turned a differential equation type of problem essentially into an integral type of problem. And we'll see why. So we use this formula then. U1 is equal to negative integral y2 times f over the Wronskian of y1, y2, right? And u2 is equal to the integral of y1 times f. Notice no negative sign out here, divided by the Wronskian of y1, y2. Okay, and this negative sign out here, important to remember. So, okay, so first things first, this obviously only works for second order differential equations, right? So, second order diff EQs. You can generalize this to higher dimensions. I'm not going to bother because this is an optional topic anyways, but in second order differential equations, you use this variation parameters. So, and this integral formula only applies to second order diff EQs. So, okay, so what are the parts, right? F of x is always the right-hand side, right? So f of x, f is the right-hand side of the original diff EQ. And the Wronskian, right, wy1, y2 is the Wronskian. So if you remember, this is y1, y1 prime, and then y2, y2 prime, and you take the determinant of that, which is the square brackets. Okay, and cover this in class, I think, 2-3 weeks ago when we introduced diff EQs. Essentially, it tests for linear independence of your homogeneous solutions, but here we can use it in this integral. So, okay, so if that's the case, then what we want to do is we want to find what the Wronskian is. Right, so that's going to be a derivative, and then y1 is e to the x, and y2 is e to the 4x, so e to the x, e to the 4x. Derivative, e to the x, derivative here, 4 e to the 4x. Okay, and then the determinant is going to be 4, or it's going to be e to the x times 4 e to the 4x minus e to the x times e to the 4x, and that's equal to 4 e to the 5x, because you add the exponents, minus e to the 5x. So we get 3 e to the 5x as the Wronskian. Okay? So now, if we solve for u1, right, what is that? Well, okay, it's negative integral, and then y2 is e to the 4x, all right, times f, which is 7x e to the 4x, divided by the Wronskian, which is 3 e to the 5x. All right, and so this is negative integral, this is 7/3, and then here you get like x e to the 8x over e to the 5x, which is negative, right, 7/3, take that out front. This is really x e to the 3x. All right, so you get this integral, x e to the 3x. It's not the best integral. You actually have to integrate this one by parts. So I'll do one here just because. So we're going to use a different color. Let u equal x, dv equals e to the 3x. All right, du is equal to 1. dv would be 1/3, or v would be 1/3 e to the 3x. And then the integral is equal to uv minus v integral v du. So that's equal to 1/3 x e to the 3x minus the integral of v du, which is 1/3 e to the 3x. All right, so now we see that this is then just 1/3 x e to the 3x minus 1/9 e to the 3x. Okay, so that's the integral. And so now this is negative 7/3 times that integral. So 1/3 x e to the 3x minus 1/9 e to the 3x. And so we're going to see that we're going to get negative 7/9 x e to the 3x plus 7/27 e to the 3x. Okay, so that's u1. Okay, so that's all of u1. Cool. Then the next part is to find u2, right? And u2 is equal to the integral of y1 f over the Wronskian y1, y2. Okay, so that's equal to the integral of e to the x times 7x e to the 4x divided by 3 e to the 5x. This integral is so much better and so much easier to do. You get 7x e to the 5x over 3 e to the 5x. So the e to the 5x cancel. You get 7x over 3, and that's really then just 7/6 x squared, right? And that's going to be u2. So u2 was a very nice integral to calculate. u1 was a bit nasty, but hey, you win some and you lose some, right? So, okay, you have your integrals that you solved, and you have u1 and u2. So now you want to plug that back in, right? So step 4, or I guess this is still step 3. So yp is equal to u1 y1 plus u2 y2. So that's negative 7/9 x e to the 3x plus 7/27 e to the 3x. y1 was e to the x, and then plus u2, which was 7/6 x squared times y2, which is e to the 4x. Okay, and then simplifying this, you get negative 7/9 e to the 4x, or x e to the 4x, plus 7/27 e to the 4x, plus 7/6 x squared e to the 4x. So almost there, right? This is almost correct, except we have 3 terms in our particular solution. And if you remember last week, or even with this guess up here, right, if you use the annihilator guess, you would only have 2 unknown coefficients, right? But for some reason, we have 3. So what's the problem? Well, the problem is this guy right here, 7/27 e to the 4x. This is really c e to the 4x, right? And where is that? C to the 4x is in the homogeneous solution. So it's fine if it pops up in the particular, because all we have to do is just get rid of it. So this is c in the 4x. It's already in the homogeneous. So the correct then particular solution would be actually yp is negative 7/9 x e to the 4x plus 7/6 x squared e to the 4x. So this is the correct homogeneous. You just the correct particular solution. You just drop any homogeneous parts that show up here. They're harmless. So okay, so that's what we get. And yeah, if you remember last week, this is what I told you that you should have gotten as the answer to your diffie-q. And here's just a different way of approaching it using variation parameters. Okay, one thing I want to talk about real quick then is right here, right in this integration. So when using variation parameters, so this is a very important note. So remember, variation of parameters solves for the particular solution, right? And in the particular solution, remember, all our constants are going to be found, right? So we explicitly show this in annihilators, right, where we set up these unknown constants a and b, and then we eventually like solve for a and b, right, of the particular solution. Variation parameters, the same thing happens, right? We get actual constants. Well, that's not what I wanted to circle, but we get actual constants in our particular solution. So because we're solving for the particular solution, we get our constants, and so therefore when we integrate here, right, when we're integrating here, we don't need the constant of integration. All right, this means we don't need the constant of integration for variation parameters. Again, it's because you're solving for a particular solution where all of your constants are known. If you include the constant of integration, what you're actually doing is that you're including parts of the homogeneous, inside that you guess. So yeah, we don't need it. So just don't include it when you're using variation parameters. However, just looking ahead, we're going to be introducing this method called reduction of order, okay, which is section 8.9, and reduction of order solves for the general solution. All right? It solves for the general, it solves for particular plus the homogeneous. So therefore, you need constants of integration when you're doing reduction of order because, right, the general solution includes YH and YP, and in YH you have unknowns, right? In your homogeneous you have unknowns. All we have to do is scroll back up to YH right here, and you see that we have unknown constants or unknown coefficients, right? So keep that in mind. Variation parameters, the method we're doing right now, or that I just showed you with this integration right here, we do not need to add constants of integration, right? We don't need these plus C's, right? We do not need to have them, okay? So don't include constants of integration in variation parameters. And reduction of order, because you're solving for the general solution, not the particular solution, you will need that in the future. So if you're wondering about that, this is a really big deal because if you, in reduction of order, if you forget the constant of integration, you're just going to get a wrong answer. But in variation parameters, if you forget the constant of integration, it's fine. If you include the constant of integration, that actually ends up being not a problem because it ends up being a homogeneous solution in the particular that you just drop at the end. But anyways, keep this in mind. And so, okay, besides that tangent, then step 4 is to find the general solution. So to wrap this one up, you get y of x is equal to yh plus yp. Okay, where here's yp, we have that circled, and then yh is the homogeneous found in step 1. So, okay, that's variation parameters, that's how you use it. And why would I introduce variation parameters now? So again, you get to use integration rather than taking product rule. So if you prefer integrating by parts, it's better to use variation parameters than to use annihilators or the method of undetermined coefficients. So I personally actually do enjoy using integration more, so that's why I want to introduce this. The other reason why I introduced this was because if you notice how we solved for the particular solution here, right? u1, y1 plus u2, y2. Notice that we have no functional form assigned to what y1 and y2 has to be. So what that means is that its variation parameters is very flexible in that I don't care what my right-hand side is, right? So in all of the problems that we have given you so far, the right-hand side has always been something that looks like this, or something that has sine and cosine terms inside, right? But let's say I give you a differential equation that doesn't have sine or cosine, and doesn't just have e to the x on the right-hand side. So for example, let's say we take a look at the following differential equation, right? Y double prime minus 6y prime plus 9y is equal to 4 e to the 3x ln x, right? So this ln x term in here makes it impossible to use annihilators or the method of undetermined coefficients to solve this problem, right? However, because we're in variation of parameters, right, notice how we solve for u1 and u2 is that we integrate the right-hand side. It doesn't matter if the right-hand side has an ln inside of it, right? You can always integrate natural log. So because of that, variation parameter is very strong in that you can, whatever your right-hand side is, it doesn't matter because as long as you can integrate the right-hand side, you can integrate and get the differential equation solution. So let's take a look at how you do this problem. So step 1, right? It's the homogeneous. So this is d equals 3 multiplicity 2. So you get YH is going to be C1 e to the 3x plus C2 x e to the 3x. It's fine. So step 2, right? You have to guess YP. And for annihilators, the thing is we can't. Right? So you can't do it. The ln x makes it impossible to do that. So under variation parameters, we see that, okay, right, yp is equal to u1 y1 plus u2 y2. Okay, and what's y1 and y2? Well, that's going to be y1, this is going to be y2. Okay, so step 3 is to solve for u1 and u2, which then becomes the following. Remember, so u1 is, or the first step, or you can write the equations down at least. u1 is equal to negative integral y2f over the Wronskian, y1, y2, and then u2 is equal to the integral of y1f over the Wronskian, y1, y2. All right, and then, okay, so let's solve for the Wronskian. Wronskian y1, y2 is the determinant. So y1 was 3e to 3x, and y2 was x e to the 3x. So the derivative is 3e to 3x, and then this derivative, it requires the product rule. And you should get 1 plus 3x times e to the 3x. All right, so we take this determinant. You get e to the 3x times 1 plus 3x e to the 3x minus 3e to the 3x times x e to the 3x. So this becomes 1 plus 3x times e to the 6x minus 3x e to the 6x. So this term and this guy kill each other, and then you get e to the 6x as your Wronskian. Okay, so now u1 is negative integral y2f, so that's x e to the 3x times f, which is 4th e to the 3x ln x, over e to the 6x. And you notice that, hey, that just instantly kills the e terms. So now you get negative integral 4x ln x. Okay. 4x ln x, this is something you should have on your cheat sheet. Or just the integral of x ln x is something you should have on your cheat sheet. And this is equal to the integral of this. Integral of x ln x is equal to 1/4 x squared, 2 ln x minus 1 plus some constant, right? But remember that we don't need constants of integration in variation parameters, so this becomes negative 4 times 1/4 x squared, 2 ln x minus 1. All right, and then so u1 looks like it's going to be x squared minus 2x squared ln x. Okay, so that's u1. u2 is equal to the integral of what y1f, so that's e to the 3x times 4 e to the 3x ln x. All right, so that's y1 times f divided by the Wronskian, which is e to the 6x. Again, immediately those die, and now you get the integral of 4 ln x. And so ln x is also something that you should know. You should either have that memorized or you should know or have it on a cheat sheet, but the integral of ln x is equal to x ln x minus x. So then u2 is going to be 4 times x ln x minus x, which is equal to 4x ln x minus 4x. All right. So that's u1 and u2. Now remember, yp is equal to u1 y1 plus u2 y2. So u1 y1, that's x squared minus 2x squared ln x times y1 e to the 3x plus u2 y2, so 4lx ln x minus 4x. And then y2 is x e to the 3x. So this is x squared e to the 3x minus 2x squared e to the 3x ln x plus 4x squared e to the 3x ln x minus 4x squared e to the 3x. So like terms, this guy and that guy, those are like terms. And then this and this are like terms. So we get negative 3x squared e to the 3x plus 2x squared e to the 3x ln x. And is that, yeah, that should be the correct particular solution. Right, and remember, always plug it into Wolfram Alpha just to double check. I'm not going to do that here because I have this worked out already and I'm pretty sure it's correct. So let's make that look a little better. So negative 3x squared e to the 3x plus 2x squared e to the 3x ln x, and we have to make sure that none of this is in the homogeneous, and it should not be. Where did my screen go? Yeah, it's not, right? C1 e to the 3x, C2 x e to the 3x. This down here, this is x squared e to the 3x, so that's fine. And then this ln x term, of course, can't be in the homogeneous. So, and then step 4, it's the general solution. So, of course, y x is equal to, or, you know, just y, or y of x is equal to yh plus yp, and yh up here, right? Here's yh, and then yp in the box down here. So, okay, so that's what I did. That's what I covered Thursday or Wednesday in recitation. And again, variation parameters, you don't have to learn this method. I just think it's cool. It's also nice to have, you know, a lot of tools to use in solving diffie-qs. And if you're someone like me who hates like chain rule and would rather deal with like an integral, or not chain rule, but product rule, and you would rather deal with integration instead, variation parameters is definitely the way to go. So, okay, that's all for this video. And I think next week in recitation, we're going to be covering the spring stuff, and I think reduction of order, which is, so reduction of order is by far the most powerful tool you're going to have in your toolkit for solving diffie-qs. And the spring stuff is just stuff I don't really like, but oh well, we have to cover it. All right, so hope you had a great Thanksgiving break, and I will see you all next week in recitation.